Hello and welcome back to Calculus 1. This is section 2.4 on infinite limits. So we're talking about limits whose answer is infinity. So we have three creatures to discuss. Limit as x goes to a value of f of x is equal to positive or negative infinity. So this is the form that we are looking for in this lecture. Now we also have those two one-sided limits that would actually lead to this. So I will say, or we are considering limit x goes to a minus, this is from the left, and then from the right, x goes to a plus. So these are the limits which we are considering. So what do we do at the end? Well, if you consider, let's say, limit of 1 over x as x goes to 0 minus, you draw the graph and you look at it. You see that when you approach from the left, when you approach 0 from the left, your y value goes to negative infinity. Limit is the y value of the function. Fancy way to compute the y value of the function. So limit is the y value, and you see that the y value goes to negative infinity as x goes to 0. On the other end, we have limit x approaches 0 plus, which now would be approach from the right, which goes to positive infinity, and by the theorem we covered last class, these two are not the same, therefore the overall limit in this case does not exist. If it didn't click last time, it must click now, and I'll write it in blood. One-sided limits always have an answer. You cannot have does not exist on one-sided limit. So one-sided limit answer is always there. We have positive and negative infinities in this case. So one-sided limits always exist. So L or n infinity. The two-sided limit, the one that is general, this one that is all in black, that one can go does not exist, because if those guys don't agree, this one does not exist. That was a big theorem. So technically we stick more to these one-sided limits because they give us answers. Let's take a look at the next example for the limit x approaches 0 of 1 over x squared. Well, I know what the graph looks like. I know what the graph looks like. So now as I approach from the left, we are going to positive infinity. So this is x approaches 0 minus. Then I have limit x approaches 0 plus, which is from the right, and we also find positive infinity. And now the overall limit, these two guys match, so the overall limit 1 over x squared is also positive infinity. So please be careful with notation. Now that I will say the devil is in the details. So these pluses and minuses here are not there for decoration. Minus means approach from the left, which is the red arrow. The plus means approach from the right, which is the blue arrow. And these guys with pluses and minuses are your one-sided limits. The one without minus and plus is the two-sided limit, which is the overall limit, which could exist or not exist depending on what these guys have. The major theorem from last class said that if the left and right limits are the same, the overall two-sided limit exists, and it's that number, or infinity in this case. If these left and right limits are different, then your overall limit does not exist. And the lecture is over with its theory. Now we are going to do the application. Application for the infinite limits is going to be vertical asymptote. So this is a concept from your pre-Calculus 1 class. Some functions have vertical asymptotes. You know that those are vertical lines, linear lines, straight lines, which function cannot cross. So the function follows that line. So now we are going to write the definition for the vertical asymptote, and then we are going to correct and improve on some things that you guys learned in pre-calculus course. Because now with more powerful tools, you can be more precise and more careful with your answers and analysis of functions. So let's go. A function f of x has a vertical asymptote at x equals a if the limit as x goes to a minus of f of x is equal to plus minus infinity, or limit x goes to a plus of f of x is equal to positive negative infinity. So this is what we have as a definition. As long as one of the one-sided limits goes to infinity at that point a, you are having a vertical asymptote at that point. Done. That's the vertical asymptote definition. Now, I did ask you before, and I'm going to ask you again, please do not study examples of calculus, because you are going to get overwhelmed and you're going to fall off the truck. Study theorems and definitions. Observe over here that this is a function, not the function, and then you have one rule for these types of functions and one rule for different kinds. No. All functions, even those that you haven't learned yet. You're going to learn a whole new class of functions in Calc 2 called hyperbolic functions. You haven't dealt with those functions yet. The last group of functions you guys learned is a group of trigonometric functions. You know, 6 of those, and then 6 inverse trig functions. So you learn those 12 functions in pre-calc 2. Pre-calc 1, you learn logarithmic, exponential, right? So you learn different types of functions. This definition doesn't care what kind of function you have. So if the problem is exponential, fine. If the problem is radical, fine, radical function. So whatever function you can possibly come up with. And by the way, there is a book with 2,500 pages on mathematical functions, where polynomials are taking, you know, 1 page. So the field of mathematics is crazy rich with functions. And so far you probably know 0.003%, and I know 0.01%. That's technically how little we all know combined, right? The field of mathematical functions is insane. The beauty of the red statement is, I don't care what kind of functions we have on the table. If the limit works out to be infinity, it has the vertical asymptote at that point. So, no special cases, no exceptions, none of that stuff. So now, if I consider f of x equals 1 over x, and I consider the limit we just did, x goes 0 minus of 1 over x is negative infinity, that spells vertical asymptote at x equals 0. This is how you use theorems and definitions to solve problems in calculus. And the entire calculus is like this. As soon as you start studying examples, you are doomed. Because if you learn a certain concept in calculus, and you learn it only for polynomials, and I hit you with exponential equation on the exam, you're just going to stare at it and quit. Because you have no clue what to do. You didn't study the theorem which said a function will behave this way. You studied an example which is one example of 5,000 you can come up with. So the algebra approach will not work in calculus. You have to learn stuff in red. And stuff in red gets applied to every single function that is out there. Now let's take a look at another example. And this is one of my favorite examples, obviously, because it fixes the issues and problems that you might have picked up in your pre-calculus course. We are going to consider function f of x. Let's go with x minus 3 over x squared minus 9. So if you are to put your pre-calculus thinking hats on, and I ask you about the vertical asymptote or asymptotes, what would you say? What was the way to find vertical asymptotes in pre-calculus? Does anyone remember? Yes?
It needs to be more of the equation. Like that's just the first part.
No, well, this is the function. The question is, do we have any vertical asymptotes there? And what was the pre-calculus way?
I think I would put that one as 1 p.m.
This is a rational function, yes. X equals 3, negative 3. Okay. So, pre-calculus teaches that you're supposed to set denominator equal to 0. Because when denominator is 0, you have vertical asymptote. Well, unfortunately, we have to kill that thinking now. So, pre-calculus says, set denominator equal to 0, and there go your vertical asymptotes. No. Because we'll see now in this example. We are still going to set denominator equal to 0, and we are going to get candidates, the positive and negative 3, as you guys noted. So positive and negative 3, both of these numbers will make your denominator equal 0, and we know we can't compute when denominator is equal to 0. So now what do we do with that information? Well, the pre-calculus says you should have a vertical asymptote at 3. Let's check that. So I'm going to find the limit x approaches 3, and I'll put minus from the left, because I get to pick one of the two from the red definition, right? So let's put from the left of x minus 3 over x squared minus 9. And the way to solve this, we see that we can factor and cancel. Learned this last class. So I have x minus 3 times x plus 3. And that's 1 over 6. Right? Is this infinity? No. Let me write that in blood. 1 over 6 is not positive or negative infinity. So, no vertical asymptote at x equals 3. It didn't fit our theorem up there. So we just learned that pre-calculus lied to us. Well, no, we just didn't give you the whole picture. We avoided examples where this stuff happens. Conveniently gave you only the examples that work in the realm of setting denominator equal to 0 and getting your answer. Now, you have more powerful tools. Your pre-calculus claims vertical asymptote at 3. You do the limit. You didn't get infinity. And calculus says, sit down. Right? It's not an asymptote. Let's check the other number. The way we check is we run definition again. So, limit x approaches negative 3 minus, from the left, right, of x minus 3 over x squared minus 9. Cancel again. Limit x approaches negative 3 minus x minus 3 over x minus 3, x plus 3. This cancels, and we get to the statement like this. Now we can't plug in, because when you plug in you get 1 over 0, right? Last class we learned that if you get 0 in denominator, walk away. Walk away fast. So what are your options? Well, graph or a chart, right? We should know how to graph this by hand. What would this plus 3 do to the graph of 1 over x, which is like this? What would this plus 3 do? Shift to the left 3 units. Very good. So your standard graph is going to be now shifted to the left to -3. And as you use your eyes to look at the problem and see that as you approach -3 from the left, you are going to -infinity. So x equals -3 is a vertical asymptote, because you got the infinity. That satisfies our definition for vertical asymptotes. So now you can finally have the clear picture for f of x equals x minus 3 over x squared minus 9. This particular function has open circle at 3, 1 over 6, which means no value there. It's a hole in a graph. And it has vertical asymptote at x equals -3. We can actually graph this now easily. So here are the two specs that I have. I have a point, which is open circle at 3 and 1 over 6. That was calculated with the first limit we did, where the answer, when the y value for 3, limit at 3, came out to be 1/6. So that creates a point 3, 1, 6. It creates a point that doesn't exist because it's in denominator, right? So it's 0 in denominator, so you can't have a value there. And then the second line that I have at -3 is the vertical asymptote from the second calculation. So now I draw the graph quickly. I have to draw my 1 over x graph. And as you can see, the graph has the vertical asymptote at -3 and open circle at 3. Now, if you want to verify something like this on your graphing calculator, which you are not allowed to bring in on exams, you will you will graph it, and then you will zoom in to the value that you're interested at. I did this in class on Thursday. Oh wait, no, they had a different. By the way, I don't use any notes or anything. Whatever function I put down, I use. So now I have to flip this. So you have x minus 3, and then x squared minus 9. Enter. Okay. So zoom standard. All right. So document camera. So if you graph this on your TI-83 or 84 or whatever you have, and you keep your window 10, 10, 10, 10 around, right? This is what you're going to see. And you clearly see, well, you clearly can't see anymore, there it is, that there is no vertical asymptote. For starters, you see that there is no vertical asymptote at 3. You only see the one at -3. The next part is to zoom in at value 3, and you will see a missing pixel. So one of the pixels will not be lit anymore. So I'm going to now go change window from x minimum 2 to x maximum 4, and y from -1 to 1, and graph that. I hope that you see a missing pixel above the tick mark, right? That's the open circle, which happens at 3, 1 over 6. So 3, 1 over 6 will have an open circle there. All right, 30-second timeout. I mentioned that you can install these calculators if you are running right technology, right? Yeah. If you have Apple garbage, throw it away, get real stuff, and then you can do things in life properly.
What's the alphabet?
I will write it because it's nothing that you can actually say. It's a webbing emulator. A webbing. Yeah. Yeah.
Oh, webbing in the email? Okay.
Emulator, yeah. All right, great. For certain functions, it just pays to know what they look like. For instance, f of x equals ln of x would have a vertical asymptote at x equals 0. The function would look like this, going through 1. And in this case, if you write limit of ln x as x approaches 0 minus is going to be negative infinity, implying vertical asymptote at x equals 0. Oh, let me show you the way how you can make it so that I don't like you. If you write this, I will hate you forever. Because this has no meaning in mathematics. This is just writing random garbage. That VA equal to 0. This is equation of the line. Your horizontal line is y equals a number, and your vertical line is x equals a number. VA equals to a number is meaningless garbage, and it will be graded accordingly. Followed with me being allergic to you for the rest of the class. So please pay attention to that. All right? So this is the proper way to write things. Vertical asymptote at x, or you can spell at, right? Or you can write this, email at, I don't care. So vertical asymptote at x equals to 0. And with this, the lecture is over. Yay. Bye.